there are a lot of cool patterns in Pascal's triangle. So, first of all, did you figure out these ones were 5s? And these were 15s? And 1, 7, 21, 35, 35, 21, 7, and 1 for row 8. Did you notice the following pattern? That if you add the 2 above the number, it equals the number underneath. So if you wanted to do the next row, you could have a 1, and then 7 plus 1 is 8, 7 plus 21, 28, 21 plus 35, 56, 70, 56, 28, 8. And this 1, it works this way too, because 1 plus, oh, there's nothing here, so 1 plus 0 is 1. That's why the outside stays a 1. So this is Pascal's triangle, and it has a ton of characteristics. Like I said, if you want to watch one of my previous videos, you can see some of the cool patterns that are in here. What we're going to do is turn to part D, and notice that all of these numbers are combinations. If you did 4 choose 0, you would get 1. If you did 4 choose 1, you would get 4. If you did 4 choose 2, you would get 6. 4 choose 3 is 4. And 4 choose 4 is 1. And that's a row of Pascal's triangle. And what we're going to notice in 8.6, so we'll open that up right away as well, maybe. We're going to notice how we can use this triangle. Well, let's do this getting started first. If you've got a random row, there's a couple of ways you can figure out which row this is in Pascal's triangle. Okay? So if we go back to our Pascal's triangle on the previous one, and look at the different rows, I like to use that number to tell which row it is. Okay, so that number is a 4. It happens to be row 5. So on our example here, I have 11. I know it's going to be row 12. If I count how many terms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Row 12 has 12 terms. Row 1 had 1 term, row 2 had 2 terms. And this 11 would be 11 choose 1. So then I could take another number like this 330 and say it's going to be 11 choose 2, 3, 4. And if you type 11 choose 4 on your calculator, sure enough, you get 330. Now what we're going to do with Pascal's triangle is connect it to algebra. So permutations and combinations so far has been all about counting things, and now we see how those ideas of counting connect to algebra. So, to start off with, if you did x plus y to the 0, anything to the 0 is equal to 1. If you do x plus y to the 1, well, that's just x plus y. Technically, you have 1x plus 1y. If you do x plus y squared, you would get x x squared plus 2xy's plus y squared, and technically you could put 1's in front of the x squared and y squared. Do you see what's sort of happening with the blue numbers? If I do x plus y cubed, I'm going to get 1x cubed. And then I'm going to get 3 x squareds and a y. And then I'm going to get 3 xy squared, and finally I'm going to get 1 y cubed. The numbers in front, when you multiply this out, happen to be Pascal's triangle. If you had to do x plus y cubed using your previous skills, you would have to do x plus y times x plus y times x plus y. And then you would say, well, I know how to multiply x plus y times x plus y. I could FOIL that and get x squared plus 2xy plus y squared, and I still have to multiply by x plus y. And then you would have to do all of these arrows, right? And combine your like terms, and you get 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. And a pattern starts to happen. We start to see Pascal's triangle. And if you did x plus y to the 4th, if you did it the old way, you'd have x plus y times x plus y times x plus y times x plus y. And since 2 of them you already know is x squared plus 2xy plus y squared, you could do that. And then you could arrows from the first one, arrows from the second one, arrows from the third one, and multiply all 9 of those out, combine your like terms, and if you did that, you would find you would get 1 x to the 4 plus 4. What do you think my variables are going to be for the second one? Do you see the pattern? I know that you see the pattern with the blue numbers being Pascal's triangle, but do you see the pattern with the variables and their exponents? You're going to have an x cubed and 1y. Next, I'm going to have a 6. And what are my variables going to be? X squared and y squared. And then I'm going to have a 4 again. And this time I'm going to have a y cubed and just 1x. And finally, I'm going to take this part of, not that part away, I'm going to take these arrows away. I'm going to explain something that's happening when we multiply 4 things together, like x plus y times x plus y times x plus y times x plus y. There's a lot of there's a lot of stuff happening when you multiply it all out. But when you multiply it all out, there will be terms, because of all the arrows, there's going to be a term where you choose just all the x's. And there's only one way to do that. Because if you have to pick one from each bracket, there's only one way to get all 4 x's. But if you want to get just 1y, could you see that you could get the 1y either here? So you could have done all 3 arrows off. I could do this x, this x, this x, and that y. Or I could do this x, this y, and this x. Or I could do this x, this y. Or finally, I could just start with the y and then do the x's afterwards. Can you see that there's 4 options? Basically, how many y's are there? 4 of them. How many did I choose? I just chose 1. 4 choose 1 is 4. This one has no y's. 4 choose 0 is 1. This one has 2 y's. This is 4 choose 2. Then I have 3 y's. 4 choose 3 is 4. All 4 y's. 4 choose 4 is 1. So a little explanation of why the combinations comes out in the binomial expansion. And what we're going to have to do is we're going to have to expand a bunch of these. So here is our first example. Expand and simplify 3b minus 1 to the 4. So first of all, I'm going to put a little Pascal's triangle here. And the first pattern I want you to notice is whatever the exponent is, so this time our exponent is a 4, that means that your expansion is going to have 5 terms. So in Pascal's triangle, I'm going to go to the row with 5 terms. So 3b minus 1 to the 4 is going to equal, the first thing I'm going to do is space it out and write the ones 4, 6, 4, 1. Because I know that it has 5 terms, and from Pascal's triangle, the coefficients are going to be 1, 4, 6, 4, 1. Next, my term 1 is a 3b. The first one would have that 4 times. The second one, 3 times. The third one, 2 times. Fourth one, only once. And the fifth one, not at all. Your second term is a minus 1. Your first one doesn't have any minus 1s. The second one would have minus 1 once. Then minus 1 twice. Then minus 1 3 times. And finally minus 1 4 times. So that's the pattern in the variables. Now we have to simplify. Well, to the exponent 4th, 3 to the 4 is 81. B to the 4 plus 3 cubed is 27 times 4 is 108 times a negative 1 will be minus 108 b cubed. 3 squared is 9. 9 times 6 is 54. Negative 1 squared is positive 1. 54 times positive 1 is plus 54 b squared. 4 times 3, negative 1 cubed is negative, so this will be minus 12b. And finally, negative 1 to the 4 is positive 1 times 1 plus 1. And this is a lot faster than writing 3b minus 1, 3b minus 1, 3b minus 1, 3b minus 1, and multiplying it out otherwise. So noticing this pattern lets us expand these binomials faster. Questions for practice on this one are 3 and 4.